So our next speaker will be Frank, who is he's also one of the developers in the SciML ecosystem, known for recently doing a Google Summer of Code in DiffEqSensitivity for methods for differentiation of chaotic and hybrid systems, and he'll be talking about the work that he did there. So take it away, Frank.
Yeah, thanks for the kind introduction, Chris. My name is Frank, and I'm a PhD candidate in the group of Christoph Bruder at the University of Basel. And the talk today will be split into two parts. So in the first part, we will treat these interesting chaotic systems where very nice features emerge. And you can already see these things in simple systems, such as classical double pendulum, but also in fields like fluid dynamics or climate models, you can see these chaotic behaviors. And in the second part of the talk, we will come to hybrid systems. So those are systems which are have some discontinuities in the time evolution. So for example, we can have could have a kicked oscillator, or like discrete switching time controllers, or also in pharmacology, one could consider models with some explicit dosing times. And just to recap for what ordinary differential equations and sensitivities are, an ODE can be written as this initial value problem where we have the ODE function that contains some parameters theta, and y would be the state of the differential equation. And then we say the initial value is the state y0 at time t0. And then typically we're interested in optimizing some form of loss function, where the loss function maps basically the state and the parameters to some real number, quantifying our objective. And then we're interested in saying how this objective changes when we change the parameters or also the initial conditions. And this is what we will call basically computing the sensitivities. In this talk, the main idea will be to show this kind of failure for conventional sensitivity methods in the case of chaotic dynamics, and discuss alternative methods which we can use instead, and also discuss what we have to do if we have these kind of discontinuous events inside of this ODE. Now for this, it's first useful to recap what sensitivity analysis is about. I mean, more in a nutshell, but the easiest way to think about it is basically to write your ODE solver, at least if you want to do this discrete sensitivity analysis, inside of some package which is compatible with automatic differentiation. And then you can either use forward mode AD or basically reverse mode AD to differentiate the steps which your ODE solver would take. There's another approach to sensitivity analysis, and this is basically to derive explicitly the kind of equations which would compute the sensitivities for you. And so this is like if you differentiate the ODE respect to the parameters, you end up with these so-called forward sensitivity equations. And very similarly, but a bit more involved, is maybe the computation of continuous-adjoint sensitivities, where you also derive basically a set of ordinary differential equations which allow you to compute the sensitivities with respect to the initial state and the parameters. And here I just want to point out that depending on the choices of the computation of recomputing the initial state, which is needed for this vector Jacobian product here, or how to compute this integration part, you arrive at basically different methods. Now let's see or basically introduce what chaotic behavior is about. And we will do so for the Lorentz system, which is a simplified mathematical model for atmospheric turbulence. And so the model has basically here three coordinates or states, so x, y, and z. And we have three parameters, sigma, rho, and beta. And for the rest, here you can think that we fix sigma and beta and just look at the variation with respect to this parameter rho. Now, one of the fun features is that if we start at some initial condition here and we solve this Lorentz system forwards in time, and we do so by doing this 2 times with different floating point accuracies. So 1 times we solve it with float 32 and once with float 64. Then we will see that at the beginning of this time trajectories, the 2 solutions basically agree. But then after some time, some of these oscillations, we see that the trajectories diverge. And this is a very common feature. We could at first maybe think that this is just due to the use of a specific solver, but you can actually also check that even if you use a very high order integrator with very small tolerances, and you just include a small perturbation to the tolerance, you will you solve it 2 times, one with this small tolerance and one with the same tolerance basically, but just a floating point perturbation. You will also get this kind of picture where the trajectories basically diverge after some time. And a bit more thoroughly, you can use tools from uncertainty quantification, where you basically map this kind of ODE system to some stochastic differential equation. Then you solve an ensemble from the stochastic differential equations over time. And what you would see here is basically the z-coordinate of the Lorentz system as a function of time. And for some initial time, all of those trajectories from the ensemble will basically follow the same kind of trajectory. But then after this characteristic time, which we call the Lyapunov time, we will see that basically the solution after the time is random on this attractor. So we can't predict then the future anymore. In more popular media, this would be called the butterfly effect, simply indicating that like a small uncertainty in the initial condition will propagate to a very large change in the long-term future. So we simply can't predict the outcome precisely after a long time. Now, there's one nice feature in this is that if we consider a long-time average quantity, so we define our loss function as this limit of a time average, so where we here simply integrate some instantaneous loss function over time. And in addition, let's assume ergodicity, which simply means that this long-time average quantity shouldn't change as a function of the initial condition. So each initial condition should yield the same long-time average quantity, such that it only depends on the specific choice of parameters. Then for the Lorentz system, we can, for example, check that if we solve the system forwards in time and plot here this z-coordinate as a function of the time, then it has these strong oscillations, and the time average would here be, for example, this red line. And we can repeat this average computation for different values of the parameter rho. And it turns out that this actually has a kind of very smooth behavior. And if we stare at this plot a bit longer, then we will actually see that the slope of this objective with respect to the parameter rho, so the derivative, will actually be close to 1. So we might think that we should be able in principle to just do sensitivity analysis on this objective and estimate this slope. However, if we now apply these kind of conventional sensitivity methods like automatic differentiation or also just doing finite differencing, we see that these sensitivities are several magnitudes of order wrong. So we see here either a way too small value or like a way too large value. And in fact, it can be shown that this this explosion of the sensitivity can be linked to this kind of Lyapunov time, or differently speaking, to the Lyapunov exponent. And so basically the Lyapunov exponent would indicate how strongly these kind of sensitivity tools diverge then. The maybe most intuitive solution to still compute sensitivities by these conventional sensitivity analysis methods would be to basically try to average these largely fluctuating values or diverging values even over an ensemble of trajectories. And this is the so-called ensemble method. But it turns out that this actually does not always work. So in general, the kind of derivative of the average which we want to compute is not the average of the derivatives. And because these tangent solutions which we would compute by automatic differentiation are not bounded but really diverge with this Lyapunov exponent, we actually can't interchange the limits. So we're not, technically speaking, here allowed to swap the long time behavior and the sensitivity computation. So the important question which you should ask at this point is, so the trajectories, though they diverge, and I mean the position on the attractor is essentially random, you still see that they kind of have the same behavior, right? So they're not going completely crazy, but both trajectories actually still lie on the attractor. And actually this fact is guaranteed by the shadowing lemma, or a bit more specifically, we can state the shadowing lemma as saying that there are actually initial conditions, so small perturbation to your system, which follow the true trajectory or the first numerical computed one. So not all of these trajectories will diverge, but there will be like a shadowing direction, like a direction or another solution that follows closely the first numerical solution. And the general idea is then, since this solution exists, it can be used to basically distill the kind of long time effect, which we just saw. So the effect that shifting rho basically increases the z coordinate, so it shifts the attractor up and down from the two effects which are combined in the first place. So we have this chaotic butterfly kind of effect and this shift of the attractor. And by finding this shadowing direction, we can basically just distill this long time effect. And the main idea is to replace the initial value problem then by an optimization problem, which simply tries to bound the norm of this diverging trajectory. And in fact, it turns out that this is then a well-conditioned problem. And since we can bound the norm by L2 norm, it's an least squares problem. Yeah, this method actually is then guaranteed to converge as a function of the square root of the time if the system is ergodic and if it's hyperbolic. However, the kind of this most easiest still method for these shadowing techniques still scales rather poorly with respect to the number of states and time steps, and so it's numerically rather expensive to do. More sophisticated methods then actually build on the same intuition, so you still first solve a numerical trajectory forwards, which is your reference trajectory, and then you find this kind of shadowing direction following the first one. But instead of scaling with the number of states, you can show that you can do something more efficient and derive a scaling behavior with respect to the number of positive Lyapunov exponents. And yeah, applying these systems in the SciML ecosystem will then basically boil down to just switching the sense-alt argument in the solver, and you will see that then these kind of expected sensitivities of around 1.0 will be returned. Yeah, now we come to the basically second part of the talk, where we investigate hybrid systems that are these systems which have a discontinuity in the time evolution. So as an example, we can consider a kicked harmonic oscillator, where which is written in a general form here for harmonic oscillator that can be written as a state and a velocity. And yeah, we basically assume that we have kicks to the velocity at some fixed time points. And so you see here that then in this picture of time evolution, you simply have then kicks here leading to this kind of discontinuous time evolution. And this is one of the most easiest form for actually having this kind of event inside of the trajectories. And in general, we can have either explicit events, so ones as here above, where the condition that the event happens just depends on the time. So for example, on a regular time grid, or we can have implicit events where the condition that the event happens does not only depend on time, but also on the current state of the system. And the main part in this second part will be that we now basically implement a correction term such that you can model these hybrid systems and compute derivatives within the continuous-adjoint sensitivity methods. As an example, we can consider a bouncing ball where we have this set of differential equations and some initial conditions for the initial height and the initial velocity. And we will essentially let the ball drop. And then after some time, which is the event, is basically happening when the ball reaches the ground. So at z equal to 0. And the effect of this event will be that, well, the position essentially stays the same instantaneously, but the velocity of the ball will flip. And essentially, if it's an inelastic bounce, then we will have here a damping factor. since this is a rather easy system, we can solve for this time trajectory analytically. And yeah, the solution is given as this form, just depending. So the event time will depend on the initial velocity and the initial height and this gravitational constant. Now you can ask, well, is this bouncing ball actually now this first form of an explicit event that just depends on time? Because, I mean, we can just solve it. Or is it an implicit event which depends on the state? Because, well, we say something like z should be equal to 0 when it hits the ground. And indeed, once we have solved and basically insert the numerical values for the time evolution, in a forward simulation, we would not see any difference here for these fixed initial conditions. So the trajectory for the z-coordinate and the velocity as a function of time would look the same basically here for both of these callbacks. However, now, if we really go forward and treat the bouncing ball as this explicit event, note that the impact time essentially is fixed. So different configurations for the initial conditions or the parameters will necessarily lead to a different impact time. So the ball could in principle bounce before it actually hits the ground. And the analytical solution for the trajectory looks like this, where essentially I just inserted here the specific value of this event time computed from the numerical values we assumed. And sensitivity analysis would tell us now, for example, how the height of the ball at the final time would change if we slightly perturb the initial height. And we see here that we can basically read off here that the sensitivity would be 1 in this case of modeling the ball with an explicit event. Now note that when we do the full modeling with the kind of implicit event, where we say that the ball hits the ground when the z-coordinate is 0, in the kind of trajectory of the ball, it would hit it actually then here in this example later. And so it's really important that that this impact time changes as a function of the state. And so the full analytic solution looks then actually like this. And if we take the derivative of this solution now with respect to the initial state, we actually get a different value of the sensitivity in this case. So it's indicating that we really have to include this modeling of the implicit events, and we cannot, and explicit events in particular, ignore these kind of relevant changes in the event time. The general idea is a bit lengthy to describe, but essentially for explicit events, since they are easy enough, you can just insert the correction term between individual solves of your continuous-adjoint sensitivity methods. But for implicit events, you have to consider your solver as some function which outputs not only your state, but in addition, the event time.
Sorry to interrupt, but you have 2 minutes left. Just thought I'd remind you.
Oh, yeah, okay. It's a last slide, basically. And the general procedure is a bit lengthy, but it essentially relies on this idea and then implicit differentiation. In conclusion, I presented to you this new methods for computing gradients, and specifically the new shadowing algorithms, which allow for differentiation also of these chaotic systems and these correction terms that are needed for hybrid systems. And yeah, with this, I want to thank you for your attention.
Yeah, so thank you very much. We do have a question here from the YouTube. Can you please elaborate on higher order derivatives? What is the roadmap to make the output of the AD function differentiable?
So in all of this talk, we just looked at first order derivatives. I'm not sure if there's any literature actually on combining the shadowing techniques for getting higher order derivatives. In general, in the sensitivity packages, we basically just do something like a backward over forward. And I think in principle, it should work.
Yeah, I wonder if backwards shadow adjoints, I wonder if you can if you do dual numbers on a shadow adjoint, that might give you a second derivative. That's a great question for a next step. Yeah. Yeah, and I guess another question is, given what you've been doing with the differentiability, what are some next steps that you see for SciML in this space of improving differentiability?
Oh yeah, that's also a nice one. So I really think it's just a start on all of these techniques. So we have not too many use cases yet implemented. So basically, it's literally on the Lorentz oscillator yet, and really on relying on the bouncing ball. So it would be nice to have more example for people coming from, I don't know, engineering, having their switching time controllers also being implemented in these kind of frameworks, and we see what kind of extra tools we have to add basically, or how to modify the tools here. So it's like, I think it will be driven by interesting applications basically to see what's going on. One example from my own field would be differentiating of these quantum trajectories, where you basically have an event depending on the state of your quantum system at a given time.
Yeah, so thank you very much.